Hello everyone, it's April 28th. Oh, another day, another 7:40. My God, I don't think I have enough time to even try the other problem. So the main task for today and tomorrow is definitely try to finish a term project. And yeah, and because of that, I got bogged down. I think the deadline is tomorrow evening, and I just kind of find out what topic to research into. It's going to be a 3,000 word report, so that's a long article, but that's not really something I'm worried about. I find something that's actually quite useful to my own research, so I'm actually going to try to dig a little bit deep into it. But of course, not a lot because we only have a limited amount of time. So I'll try to just dig as much as we can, and then just submit this. But let's go to today's challenge. Okay, I've done this before. Ooh, seems to be a tough one. 1 hour. 1 hour. All right. Minimum effort path. Again, so if I cannot do it, then we will. Oh, I seem to have remembered this thing. You're a hiker preparing for an upcoming hike. You're given a height 2D array of rows and columns. It represents the height of a cell. You're situated in the top left cell, and you hope to travel to the bottom right. You can move up, down, left, and right, and you wish to find a route that requires a minimum effort. The route's effort is the maximum absolute difference in heights between two consecutive cells of the route. To the minimum effort required to travel from the top left to the bottom right. Minimum effort. So do we just, I don't know, like BFS? DFS this? Oh, DFS this is going to be a long time I have to spend. Or is it like a BFS? So like for this one, I can only go to this and this, right? And for these, we don't want to go back. So we can go to this and this. This can go this and this, right? And then for this, like we don't want to go back. So this one can go to, yeah, so we'll go this, we pick one of these, and this will pick one of these, we'll pick one of these, and this will pick this. So this one I say I go this, I compute the maximum so far. So maximum is 1, this is 2, that's fine. And from here, I go here and here. I go this one, the maximum is 5, right? And I go this one, maximum is, so it's like we reach this point, what's the maximum when we reach this? Which is the minimum of the maximum when we reach this? So actually this is 2, actually this is going to be 1. And we go from 1, right? And I go here, that will be 2. Go here, well, this one we're passing in. So to reach this, we'll have this is 2, reach here will be 5. This will be 6, so this one should be 5, right? So reach this, the minimum from here is 5. And to reach this is still 1, okay? And then from this, I can go to here, so that's still 2. And from this, I can go to here, that's 5, become still 2. Right, from this, This is 5. So it's 5. There's this 1. From this is maximum, minimum is 1. And finally is 1. I'm not sure. Is that the right way? So because this is 1. And from this, so this one will be still 1. From here will be 6. This will be 5. This will be 5. Alright? And here will be 2. And then we will reach here. This one is minimum is 2. No, minimum is 5. So behind here is 5. This is still 2. And this one will be next. So we'll just say, because we would try to reach here, right? So we just say this one just go here. We can go back, but there's no point because we already visited this one already. So we don't have to go back. Wanna try? I'm gonna try this. I think it's gonna be like a BFS. Yeah, 10 minutes to try to code it up. If it doesn't work, we'll check the result. Now we'll check the result. And oh, these days, just always checking the results. Because I just don't have the mental capacity to do this. Okay, so what do? So we need, let me get a table, right? So I need to update. We need to update its minimum effort. So let's just call it, DP, okay? And let's do maximal, okay? So we say mass.inf times, ooh, wait, is this the same size? Rows equals heights dot length. So it's a square. Heights. So we just need to have n length heights. So this is times n. For this in range n, okay. And then when I say q will equal to, I don't know what is q. And what is the initial value? So initial value should be 0, right? And then what do we pass in? We check that, and then so this one come out. We have the previous one, so this one, we say we will put that one in. We'll put that one in, and then okay. So let's say dp 0, 0 is going to be 0. So q is going to be a tuple. I'll say while q all right, and then I'm only going to go down or right. That works, and we don't go up. So like here, we go here. Yeah, we have to go up, right? Huh. Yeah, like in here, if you go, and when you go here, that was the minimum to reach here. Well, to reach here, we can go this one, go here, this one, go here. And yeah, you can also get from here, right? So if we can find, hold on, I don't feel like this is right. So this can only go this, right? So this, we can go up, go this, and go this. So we go 4 directions. And then we go 4 directions. It kind of, we update, okay? And we say, well, if it's visited, so we go 4 directions. So first we'll go here, we'll have to pick 1. All right, let's go down. And then we only visit, okay, we visit this way, but every time we visit, we go the next one, we can go up, go this way, go this way, go this way, we go 4 directions. Is that what it is? Huh, doesn't seem right. Or, because the goal is to find a minimum effort ending at a certain position, right? Since the minimum effort ending here, because this can only go from here, right? So all these can be done. So this one I can do, this one I can do. So now we're asking, well, what's the minimum to go here? So to reach this point, right, we say we can use this and this to reach this point. Okay, so we get this point. How about reaching this point? That's the point we require all 4 points. Oh, okay. Look at this one. So we say this one will require this or this, to reach this. Okay, so how about this? So this will require this and this to reach this. I find I always have trouble dealing with this. Maybe it's just a DFS. A very, boring DFS. We just go as long as we can go to try to reach the end. And then we'll find a way, right? We'll reach the end, and now we have a value, and then we're just backtracking. I might time out in this. We can terminate early, right? We find a way, and then in other ways, like say so far it's bigger, then we just terminate. Maybe. Alright, I want to just submit it, but try not to look at it, and then because it's 53, I might. Alright, so this one is alright, so this is a copy from previous. So we submit this one to pass today, and then okay, so back here, let's delete this. All right. Let's try. I'm gonna try DFS, but we might also put in a DP to kind of record what's the smallest. If I'm reaching here, the smallest is already too big, and then we just don't go. Okay, so let's keep this, and then we say def DFS. So we have current IJ, right? And then we have the max effort. Max effort so far in this path. Oh, we probably need path as well. So that's going to be a set. Yeah, it's going to be a set. It's just don't do it. So we don't return anything. Okay. And then we say, we say every time we reach a new node, right? I'm at ing, and then we say if max effort that's currently is larger or equal to, right? So maybe this is it's next time that we hit, right? If it's larger or equal to dp ij, right? If it's larger or equal to dp ij, that just means the effort we have accumulated so far is already, it won't be better. So I say in this case we just return. Okay, all right. Otherwise, if it's smaller, then we say dpij, we update dpij. Okay, so dpij equals max effort, and then we're gonna go if it's larger than this, then return, and this one, right? And then we say if I is equal to n minus 1 and j equal to n minus 1, then we return. Right? That just means we have to go to the end. Okay. Now what? So now we're gonna go 4 directions and just say for didj in 0, 1, doesn't matter, 0, minus 1, 1, 0, and minus 1, 0. Actually, why don't we just go, yeah, I always like doing this. So ninj, ninj equals I plus di, j plus dj, okay? And we say if 0 smaller equal to ni smaller than n, and 0 smaller equal to nj smaller than n, and ni and j not in path. Okay, it cannot be in path. Hold on, let me think. So when we visit my current node, I add my current node to it, right? And then we try to go to the next one. And then once I'm done, so I need to say I need to add my current node to path. I'll add, let's say ij add to it. So if it's like that, right, it's within, then say dfs ni and j, the maximum effort, right? Because this has to be the maximum effort, is the max effort previously, and heights ni and j. It's the absolute difference, right? Yeah, minus heights ij, and then we do the abs. Right, so if that, I do this, and then we're done, we go back to the next one, to the next one, next one. Once we're all done, path.remove ij, then we're done. Okay, so we'll go to dfs to go through the entire thing, and then we're going to return dp n-1 and n-1. So this kind of just iterates through all possible scenarios. So this one I think is 2. This one shall be 1. And this one shall be 0. And we have heights, minimum efforts. Huh, what the heck? Infinite? What? Huh. Maybe it should be like this. Oh, Still not right. Alright, let's go through this a little bit. Let's print ij and then maximum output. Oh shoot, I forgot to run it. Huh. My god. 0, 0, 0. And a set. Ah, now we don't have to do this. Missing 1. Path. Oh, I forgot the path. Yep. Oh, this is going to be slow. This is going to be very slow. This might be wrong. Oh. Huh. Okay, try this. This is a very naive solution. And it's wrong. The heck? Output 0. What? Shall be 9. There's only one row. Oh, what the hell? Zero, zero, zero. Oh, shoot. I thought it's the same. My bad. So I is M. List out of range. Of course it's out of range because this has to be M. And this has to be M. I don't know, I had the impression that, you know, it's all the same. Apparently it's not all the same. I thought it's a square. Generally thought it was a square. Oh, list out of range. How? Oh my god. That's my bad. Sorry. I don't know what this one is. 6. Yeah, it was just a mistake. Did not improve at all. Ah, naive solution. Didn't work, huh? Okay, naive solution does not work. What else can you summarize? Well, great. All right, I don't know. Oh my god, union find again? Thanks. Okay. I guess we're dealing with graph. Why didn't I thought about this go to graph? Okay, so we have graph. So let's say these are just the cells, and the edges are the difference. You know, the weights of the edge is the difference. Okay, that's fine. 5, 6, 0, 0, 6, 5, 2, 2, 2, and 3. Right. So the goal is to go from this top left to bottom right, the minimum weights. Ah, I see. That is Dijkstra. That is Dijkstra. Okay, so I mean, I know it's Dijkstra because I saw my solution, but I just want to see it again. So this is Dijkstra. Edge weight edge width is the difference in heights. This becomes Dijkstra. Alright, can you code Dijkstra? You feel better. My god, how many times have you coded Dijkstra? You still cannot do that? Come on, don't tell me you still cannot do that. That would be very sad. So Dijkstra is we find the starting point. Don't rush me. We find the starting point, and then we push its the next node into it, right? And then we push the next node into it. Then what? Then it's going to be a heap. Then the smallest will come out. Okay. Then we go to that node, and we'll record, right, the minimum. Okay, so we'll record the minimum. We'll go to that node. Then what? Then from that node we look around. We find the smallest. Right? Not necessarily the smallest, because it's not the sum. It's the maximum so far. The minimum of the maximum so far, right? So look around, and then then we can go. Yeah. Wait, I forgot how to do Dijkstra. Jesus. Find the minimum. Yeah, we will update. We update. So we say current weight according to this is this much, and then we're going to the right, and then we pop this out, and we update the total weight that will reach the sum. Okay, so Dijkstra is this, right? We have the starting point, and then we'll keep track of the minimum weight needed to minimum cost to reach each node, right? So we have this, and then we have boom boom, its neighbors. Okay, so we find its neighbors, we put on those are the minimum cost, and then we put them into a heap, and then the smallest pop out. And from here, we'll go to the next one, right? Go to the next one, and then we go to the next one and try to update. We'll update their minimum weight. So we update the minimum weight. So we need to keep track of the minimum weights for everyone. So okay, we have the minimum weight, and then we push that the minimum weight into this already, into this as well, right? Minimum weight, and then what? And then we say, okay, I push it in, and then I push those in. Then who pop out? Whoever is in this pop-up, because whoever is in this is always reachable, right? So I can reach this, so we go here, and then from this we'll go this. So whoever is reachable currently will pop up, right? And that thing will, so from that thing we'll go to the next one again. So they will be updated, so they will be pushed in again, right? And then they will pop out, and then we try to, yeah, I think that is Dijkstra, right? So with Dijkstra we do need a DP. I think we do need these two we still need, but we're gonna use Dijkstra. Heap equals this, right? We put 0, 0 in it, and the effort is 0, right? So far 0. Okay. We say while heap actually it's while true, but is it the first time we reach? Yeah, first time we first time we reach is always the smallest. Alright, hold on. I'm not 100% sure. This is like the, I don't know, the 5th or 7th, so 6th time I'm checking Dijkstra. I just can't memorize it. Alright, well, Q is not empty. Vertex in Q with minimum distance. Yeah, it's the minimum. And then we will remove it from Q for each neighbor if distance plus, if it's smaller than what's been, we just update it. Yeah, I think I'm right. And then we'll keep going until what? Neighbor still in Q. If you visit, then we don't visit anymore, right? each neighbor v of u still in Q. Is it guaranteed every time when you visit a node, it will definitely have the smallest value? Because if we go here, and this is the smallest, and then will this become I guess I never really truly understand Dijkstra. So when you reach a node, I'll go to the neighbor. So every time a node is visited, this node can be removed. That's I think what it is. Bless you. Each time when you visit, you can remove it. I think that's the thing. So we might need a pass, right? That's the path equals set. And while heap, and then we'll always pop out the first heap and pop out. And then you know what? It's always going to be the smallest, right? So this one is smaller than. Yeah, I guess it's fine. So we pop this out. We find the next one. We push those in, right? And the next one we find the smallest coming out, and this is the one we visit, right? This is the one we visit. And then, okay. So we say distance ij equals heap q dot heap pop heap. Okay. Then what? Then we need to go through the entire thing, and then we say if this distance is if it's smaller, we push into. If it's not, then we don't. Okay. So we say for directions. Okay, for 4 directions. So path.add. So ij put it into the path, and then we say for the next one, if it's not been visited before, then what do? Then we check, right? We say the current distance will equal to ABS, this thing. Okay, so this is the current distance, right? The current effort is going to be the maximum of this one so far and this, right? And we say if current D is smaller than dP in INJ, then dP in INJ equals current D, and then heap q dot heap push. I'm gonna push current D and INJ into it because that's smaller, so we'll push it in. Right, it's smaller, so we push in. Yeah, we check off all neighbors, and once we finish, we go back up. Then we'll try it again, right? Get out the current one. Current one, when we get out, is when we visit, we put it into the path, look around, try to push the next one. Right? If nothing is smaller than whatever is already have, then we don't push into the heap. So once this is done, yeah, the problem is when this one pop up, maybe somebody later. I need to wait until the whole thing over, right? Yeah, let's wait for the entire heap is over. Then I return dp n minus 1 and n minus 1. Let's try this. Expected 2 arguments and got 1. Of course, because I forgot to push heap. Heap should be in there. Come on, man. It's M. Okay, so this one seems to be right. Or isn't this 100 by 100? Oh, that's huge. Alright, Jimbo, don't do this. Oh, okay. Are you stupid?
Why?
Okay, so we do the comparison here, but we didn't. Alright, so let's just, this is an oversight. Equals be 0, 0 equals 0. Okay, so that's, well, what should I say? This is a hint. Did look at a hint. I did see the hint that this is a. What's the runtime of Dijkstra? v plus e log v. Anyway, that was pretty bad. Yeah. Okay, so what was this thing? It runs so fast. What the hell? You're so fast. What was you? Is this some special implementation of Dijkstra? I return D immediately. Huh. So I don't have to wait. Every time we see it is guaranteed to be this. Okay. And then we also didn't use a path. Why is that? Well, the reason is we set the previous one, right? So we'll only go back if it's smaller, right? So there's no possibility of going back. And if you go back to make it, unless you make it smaller, and make it smaller, it's definitely worth going back. So that's why, okay? No need to use path. No need to use this. And then we can do it right here, right? If let's say I equals n-1, and j equals n-1, just return d. So first time, when a node is visited, so when a node is visited, but how do you guarantee when a node visited? It's always the smallest. When a node is visited, it is the smallest, the current setup, right? So, oh yeah, when it's visited, it's the smallest of the current setup. How would it be possible to be even smaller? Yeah, it's guaranteed. It's guaranteed that the effort is minimum. That's true. And then we also don't have to do this. There's no path needed. Like this. Not exactly the same, right? Yeah, that's okay. Alright, two things to note. One, we can return immediately when the lower right is reached, because according to Dijkstra, each node visited is the best way to reach that node. It couldn't be an even better way. Two, there is no need to set up a path set that records the nodes visited. Right. This is because we will not go back to a node visited before, unless we have a good reason to do so, which is going back reduces the effort. Yeah. I think Dijkstra is the standard. What was the other solution I have earlier? See, I have another like couple thousand. Look at this. Oh, binary search. Ah. The cost cannot go down. Yeah, so that guarantees. This is actually very important because Dijkstra, the guarantee is every time you visit a node, the current cost is always the minimum. That's the guarantee. So because of this guarantee, we have to make sure that the cost will never go down. But if the cost can go down, that means it is possible in the future time that the node you have visited will actually have a lower cost. So it cannot go down. And in our case, each step we're finding the maximum, right? So also the cost doesn't go down, so we can use Dijkstra. That makes sense. So what the hell is this binary search? To choose a minimum threshold so that we can find a root whose absolute difference in height between two consecutive cells of the root less equal to the threshold. What? Oh my dear Lord. So, direction, that's fine. Can reach. We will DFS to see if we can reach. Huh? What the hell? My. Wow, okay, this is good. This is very good, very good, very good thing. Oh my god. Let me try. This is actually something that we can improve based on this, right? It's interesting. So 3, right? So this is DFS plus binary search. No, we don't do this. DFS basically we're just trying to see if we can reach right? This we can reach. And thresh, we'll put it as a int, and then this will be a Boolean value. And then we just say oh, I have a threshold and then a maximum effort. Max F. Okay, we need both. And then we just say if max effort, it's called max effort, is larger than threshold, then return false. Okay, if it's smaller, and let's say if this is going to return true, right? Otherwise, path is going to add it. And we go for directions, blah blah blah, and then blah, and then thresh. Right. So if this and this, so I'll put this one here as well. Right. If this, and this, pass, and this, yeah, it's just ridiculous. Let's put it in a second line. So if return true, okay, blah blah blah, doesn't work. Now we return false. Do we need to remove this? Yeah, I think we need to remove it. Okay, remove it and return false. So that's DFS. So now we can say low high equals 0, and I don't know, just upload this. What is the 10 to the 6? Okay, 10 to the 6. Let's do this. Oh, max is 1, so we just do 10 to the 6. Right? And then what do we say? We say while low is smaller than high, and then mid equals low plus high divided by 2. And then we say if DFS is 0, 0, max effort is 0, threshold is mid, path is set. If it's true, right, then we can make high. We want to find the maximum, right? So we just say, wait, this is good, so we can push a little bit higher, right? We can push a little bit higher. So we can push a little bit higher. We say low equals mid plus 1. Else high equals mid. Low equals mid plus 1, because you see the current threshold is good. We can hit the current threshold. So I want to be a little bit more bold. So low equals mid plus 1. And then if it comes out, if it comes out, that's not good. So we want to find, we want to be, what do we want to be? We want, if this is bad, Alright, we want high to minus equal 1. So we know if low is good, then we stay where we are. And high is not good. So yeah, so we want high to be minus equal 1. And then we want the low to stay the same, which means if it's good, if the threshold is good, okay, I'll say if the threshold is not good, right? If the threshold is not good, then we high, push it down. If the threshold is good, we don't move, okay? But this way, this is biased towards low, so it could be low plus high, right? Divided by 2, which is low, and it's good, and it's nothing will change. So we need to change the mid. How about we change mid or bias it towards high, like that? See how that goes. I'm YOLOing right now. I'm not sure. Okay, this is solution 3. That is not right. What happened? Huh? What? What? Oh, I got it wrong. If it's good, if the mid value is good, oh, we want to go to minimum. So if it's good, then it should be high, should be here. My God. Right? It should be this. Right, we say if the mid passes, which means it's good enough. Right, it's good enough. So if it's good enough, then we want high to be even lower. Right, so see, that's good enough. So we want to shift high. High is mid is good. Then we want to high shift down. But we never tried. Maybe we should do this way. Right, so we say this is good, so we just keep it here. And if it's not good, that means we need a little bit higher, so we go a bit high. Okay, let's try this. Okay, this one seems to be working. Oh, it's not good. That's not good. How? Which one? Wait, hold on. It was working earlier. What? Oh. Why did I remove that? You, the dumb. I thought that was a print statement. I seriously, I thought that was a print statement. Hmm. No. I don't know. Seems to be. Interesting. Is the binary search method no longer works? I see something is wrong. There's no max effort. We just want a threshold. It's not in path, right? Then we say if one thing d okay, e equals this. So this is the max. This is the effort, right? So we say this is the effort. If e is smaller or equal to threshold, and DFS and INJ threshold and path are both as true, then we return true. Otherwise, return false. 4 but 5 are given. Oh, we need to remove one of them. Okay. Try this. Wait, it's still going. No way. What? Well, let me think. Maybe we don't remove. It's not a full backtrack. It's not a full backtrack. You shouldn't remove. Why? Because if I visit a node already, and then from there I know going forward is not going to work. I would say, well, this one going forward is not going to work. So if I visit all the neighbors, okay, so I come here this way, right? So I visit all my neighbors and they all fail, right? And then I need to return, going back to here. So return going back to here. And visiting this. So when you visit this, do you want to come visit here again? Well, the reason that it fails is because when we go from here, we start going visiting out. And then some of the path, the effort fails, right? And if we go from here, we'll come back again to this. And we already show that this to everything, this to everything, this to everything fails. And we go here. And then we know that these fail, so we don't have to go those again. Now how about this one? Well, then we are visiting the one that we visited before, right? So basically we say if we visit a node and we have found out that starting from this node, going out is going to fail. So if we know that, then we just don't visit that node anymore. I think that's what is said here, right? Yeah, you set it true so we don't visit again. Why are we not set to false? I'm having this trouble right now. We might need to see a few more. Yeah, that's what I do. This is what backtracking is. It doesn't clear. Yeah, I mean, it makes sense, right? So if we go to a node and then we visit it and it fails, right? It just means from whatever path and we go to this node and then we go for all the other paths, they all fail. So just like this one fail. But does that mean if we coming from the other direction to this one and it will fail as well? Now, it will fail for those, but would it fail for the one that I came from? Well, that's the problem. That's the question. Well, they can argue that this is where I came from, so I can go back to the starting point, right? Or you can say I can go there and then try to find one of those to go out. And that will be, it makes sense, right? So if we go like back up and we can hit the node and then we'll try to go to the end from that node. And we have visited that node already. And the only way that it's possible is going down this way, which I can now go. Then the other way I probably visited already when I was in there, right? I already visited, so those that doesn't work, that doesn't work, and I just have to keep going here, and then nothing works, right? Those doesn't work, and we just have to keep going. Eventually, we'll reach the end, and then it's not gonna work. Yep. So we don't remove. Okay. Key insight during DFS. Even if we are doing something similar to backtracking, we do not unflag, right, the nodes that have been, the nodes that, unflag the current node when the recursion and the function call ends. When DFS call ends. This is because if going from the current node cannot reach the destination, it is also impossible to go to the destination from the current node if it is reached again from some other path. So yeah, that is important just to know. Now I'll just remove this and submit again. All right. Dijkstra. It's good. I mean, yesterday we tried to write union find about ourselves. Didn't work very well, but at least we did. And today we tried to write Dijkstra by ourselves, and it's okay. It's okay. Still, man, pretty bad performance. It's like a few days in a row. All right, that will be it for today. I'll see you guys tomorrow. Adios. Oof. Crunch.